Hello everyone, I'm Kostas. I came all the way from Oxford, England to speak to you about Mantis vision, the ring, and my experience with them, and my input and the whole story, how we went from a single camera to the ring. So in the beginning, when I joined Mantis about 10 years ago, it was a case of just using a single camera to do capturing. Single depth camera, of course, has the limitation that it can only see what's in front of the frustum. So if I were to hold my hand against this light, if this light were the camera, it wouldn't see behind the hand. It would cast a shadow. The way a depth camera works, there are plenty of different technologies out there. For example, I could mention structure light, which is the one that Mantis uses, and I will go into a bit more detail on that, or time of flight, or active and passive stereo. Mantis is using the structure light where there is an infrared projector projecting some sort of a pattern into the scene in IR space. And there is another camera on the same, what's called a baseline. So let's say it's a horizontal line. Just like the eyes, you have left and right to kind of triangulate the depth. It's the same principle here. So the light projects is a structure pattern. The camera sees on the same line and makes a judgment of which pixel correspond to which, because this is in 2 dimensions. So there are some constraints, the bipolar constraints, and from the baseline, from this distance, it can make a judgment for the depth. It's quite a little bit more complicated than that, because you need to identify the unique pixel or pattern that corresponds to the pixel at XY that you are looking at. And that involves some very clever design of the pattern and some error correction. And this is what makes the Mantis depth acquisition be, I would say, having worked with quite a lot of other depth cameras, I would say it's very precise. It's not maybe as dense as some other cameras for a reason, but what you get is very precise. Now then, we said, okay, let's design something that can do a lot more. So let's try to do multiple depth acquisition in order to fix the problem of occlusions. Of course, you would need to have one camera here, a few around. It's a diminishing returns problem when you add more and more cameras. So if you just have 2 cameras, you see the front and the back, you would be getting something like 70%. Then add another one, you would be getting 85, and so on and so on. You would maybe never reach 100%, but the more the better. So all of these cameras need to be synchronized because they hit the scene with a different with the pattern, so you don't want 2 cameras to confuse each other. So that was a problem, precision timing. And then you have a problem of fixing this puzzle, because it is a puzzle. It's you have multiple views, multiple depth maps. They need to be combined in 3D space through some matrix multiplication. How this gets put together is a big problem. In the past, we've tried a few things to make sure that the data that we're getting is clear from noise, because that's another problem. For example, we've tried extraction from silhouette, which assumes that you're in the ring and you're surrounded by a blue screen, so that everything that falls within the silhouette, in the 3D space silhouette of your body against the blue screen would be kept, and everything else would be thrown away. And now we use photogrammetry quite a lot, which requires multiple views from RGB cameras. And this is, as far as I know, very similar to what Google does for Google Maps. So there is quite a lot of data in the that are being acquired by the cameras, and each one has its own small computer, and they all go to a single computer, which we call the Lord. And This is something I've been working on. How do you get all of this information into the Lord in real time, which could mean 25, 30 FPS from 16 or more cameras at the same time? Unfortunately, we can't do compression on the fly, such as JPEG or PNG or even MPEG, because they need to be decompressed really, really fast at the other end. So while a nuke would be able to compress to JPEG, the Lord itself wouldn't be able to decompress 30 FPS times 2600. It's really pushing it, and the Lord needs to do quite a lot of other things as well. So we've tried a few things like using bias space or chroma subsampling. The one that seems to be working fairly well, and remember, we only need to reduce the bandwidth maybe by 4 or 5 times, not 20 times. The other reason for it is we don't want JPEG, we don't want the DCT artifacts, is because if we're doing photogrammetry, then this would potentially kill some textures, and we need textures in order to make photogrammetry work. And you need to have good quality textures anyway in order to do the texture atlas, which we'll see later on, to make it look good. So what we do, because we've noticed that from the camera point of view, you have the ring, which is static with the other cameras, and you have the moving person. So you have quite a lot of things, of chunks of the image that don't move. So we split the image into 8x8 chunks, and we do some comparison with the previous frame. And if it's quite similar, then we send the flag for it, a single byte or a bit. If not, then we resend the information. And although this is not a great compression, it's a kind of a poor man's MPEG, but it's extremely fast. We can do, I think, thousands of frames per second, if not tens of thousands. So that works quite well. Now, the problem is, okay, so we acquired all this information from the different cameras. How do we convert into 3D? There are two options. There's the TSDF, which is the fast and cheap option, let's say, and the Poisson reconstruction. The Poisson would give you watertight meshes. So if you have a big empty space, assuming you have correct normal information, it will create a manifold around it. It will cover it. It looks very good, Poisson, but it is slow. The TSDF is very simple. Voxel space, you have, for each voxel, you have the closest distance to a surface, and from that, with marching cubes, you triangulate and you create something. So assuming that your mesh is quite dense, your point cloud is quite dense, then you will get something. Maybe sometimes it will have a hole. Maybe not. It really depends on the circumstances. But we can do TSDF now live, and a mesh optimization also live, which means that you get down to something like, if you want 10,000 triangles instead of the original 100,000 to 100,000. And now the question is, how would we do the texture? Well, it's a case of projecting what these cameras see, which, as I said, they also have an RGB camera with them in the system. So IR camera, IR projector, IR camera, and a couple of RGBs possibly. This information is acquired by the cameras, and then it needs to be put into an atlas. And we've developed some heuristics to how to blend the different views. For example, if I were to be looking at this camera and the normals of my surface are pointing this way, then the weighting would be higher than these cameras. But in general, we tend to have continuous surfaces coming from one camera and have a small edge where the two cameras blend, and so on. And if we have an empty space, and this would be empty in terms of geometry or in terms of texture, then we use algorithms to do in-painting, also real-time. In-painting, again, in geometry and in texture, which means that if I'm holding my hand like this and no camera for some reason can see my nose, then my nose is reconstructed from information around that. So let's see so this is some views from what the cameras see. So this is the point cloud from one camera, let's say. So these are all the different cameras looking at Yeah. And this is what the RGB sees. Okay, all of this is combined, and yeah. The texture atlas, as I said, we need to allocate this 2D space because our models would use a single 2D. The TSDF and the Poisson look very different. The TSDF uses patches, basically a pre-allocated space for each camera. So if you have 16, you would have 16 different rectangles, which means that from the point of view of camera and the texture, the 2D atlas, it's fairly temporal consistent, which is very good for MPEG if you were to compress an animation with MPEG. But it's not very good for textural quality because the density of usable pixels to black pixels is not very high. But with Poisson, we are in control of all of that. We can give more pixels to the face, for example, if we need, because it's a finite space. It's very hard to bring a balance. So so this is what the TSDF map looks like, and the bottom left is the in-painted area. So these are areas that are not seen, and you can see that, well, the other spaces are from the other camera. So this is Poisson. You can see that the geometry doesn't change all the time. When you have topological changes, it changes, and you get something that is in between a temporally consistent map over some frames, and then a topology changes, so something needs to change. Ideally, you want as long runs as possible for this, because the moment that you have a change, then the MPEG would force an iframe, so then you would have a waste of bytes. In a uniform mesh, it's the ultimate case where you have a constant topology. Yeah, that means that the indices, the number of vertices are the same, the indices are the same, the UVs are the same. The only thing that changes is the vertex position because the body is changing. And we do that via mapping the human form using neural networks. There's no other way. And we have the template of the human form. It is slow. The change in topology is handled. It's very interesting how it is handled, because you would expect if a human were in T-pose and then I put your hand in the pocket, you would expect that the manifold is very different now. So how does this work? Well, interestingly, my hand will still be here, but it will be in my pocket, as a mesh. So the topology is still the same. Of course, there are cases where this breaks, but if you are quite careful, it works quite well. So this is an experiment I once wrote. This is in JavaScript. I very rarely write in JavaScript, but anyway. So this is a uniform mesh that we made some time ago. So this guy is moving, and I demonstrate some of the couple of things that you could do with this. You could see that the material on his body is changing. And I can change the texture. I can do quite a few things with this technology, such as, for example, I can recognize body areas. I can say this is the face, this is the arms, and so on. It's great for MPEG. It really compresses well. We can skip frames, we can skip geometry frames and calculate the in-between through linear or spline interpolation. We can change clothes, and we can use it for physics. We can put anchors to bones so that we know that the arm is there. And it's always, this is an arm, it's not just a triangle soup. But as I said, it's very hard to do it in real time. We don't have this in real time. So at some point, 3-4 years ago, we said, okay, we get these nice models, let's do something about transmitting them, which means mesh compression. So I've been trying a few things myself. So one of the things I tried was to combine the texture and the geometry in one image and use the very sophisticated and well-developed technology, the MPEG technology, to transfer this. So just transfer an MPEG stream and no other geometry. And this is done through having these virtual views where you acquire the depth map and the color map, and then you have a way to combine them on the client using shaders and some quite exotic technology, but it is working. Performance is quite good. I can do it in real time. I would say that the quality has been superseded since then, because when we started, we said, okay, let's target X megabps, and then internet gets faster, and then you get to a point where you could do the same thing with binary compression and something else. So the break-even point, I think, has been breached so far. But this sort of technology can do really, really low bandwidth if you need to have multiple humans, but they will not look very good. So that's it's an old video, because this is ongoing research. So this shows it's basically I'm basically trying to cover the whole body into patches that are more or less perpendicular to a virtual point of view. And as you see here, this is split. This is how this thing is constructed. And for each patch, the virtual camera will record the depth map from point of view and then map it into 2D space, and then try to give to the patches that matter, such as the face, for example, more pixels. This is an old video. The different patches are more temporal consistent, so across time it moves a lot less. But now we've moved into binary mesh compression, which is, I think it works really well when combined with Poisson and mesh tracking. You saw some animation of a mesh tracked Poisson, where it was changing over 20, 30 frames, the topology was changing. And as long as you can identify, and that's a trivial problem, as long as you can identify where the topology changes, then for everything in between, you can send deltas for the vertex positions, because everything else is the same. And we use Draco for, this is a library from Google, for the iframe. So when everything changes, you send the whole geometry and everything, and then we use a delta, our own version of a delta with entropy encoding, and it's much faster and uses less bandwidth than Draco. But again, comparing apples and oranges, this is our use case. It works really well. Some other research topics also for me is we have MVX, which is a framework that we've been developing for a very long time, where you are allowed to have layers of data and filters that act on the data, and you can create new stuff. For example, tomorrow I want to create a bump map for my data so that other people can also read that and understand and do something about it, if the bump map is itself available in an MVX file. The MVX file would contain the information from a human moving, and that may be compressed or maybe not compressed. There are ways to communicate with the SDK. As far as I know, we have, well, it's C++, all of this, but we have one for Unreal Engine. And internally, it uses quite a lot of GPCPU. I can give you an example of a filter, an old filter that I've been writing, a very simple one, where you have a geometry. It doesn't have any normals, and the filter itself calculates the normals per vertex using the geometry, some cross products, some simple maths, and then you get out a normal per vertex, and that you can use it to do lighting, for example. So this is something I've been playing with. So some new layers. So some skeleton tracking I've been doing. And in the beginning, you saw an optical flow per vertex. This is a more recent. So I'm trying to build a semantic segmentation map of the human form from input from the ring. So each different color here. So what comes into this filter is a triangle soup. It doesn't have an understanding of what is where. So, and then what you get out is something like, I don't know, a few tens, 20, 30 different IDs. And this is per texel. It's not per vertex, where it says, okay, this is the head, this is the arm, this is whatever. So that also goes as information into the texture. I'm going to briefly speak about a couple of use cases and my recent work. And I think I should only speak about things that are either in public, so have been presented, or that are in kind of development for this purpose. So Giant Head is a very strange project. So we've been commissioned by this company, and we recently presented in London. So what this company wants to build is something like 30 meters tall giant made out of LEDs. This is a real project. I'm not kidding you. If it really makes it, and it happens, it will be on the news, international news possibly, and not just in one place. So I've heard that it's going ahead very well. So the idea is that you have this build, and you have humans, people, coming into the ring, being scanned, and they say something. For example, welcome to the giant, over 10 seconds. So the problem is now we need to map this to the giant so that the giant looks like it's you. Of course, you could have any shape and your face is moving and your lips are moving. It's a very, very hard problem. So how do you solve this? So what I've been doing is that I identify the head, again, through neural networks, do an unproject of the... By the way, this needs to be real time. So when you're being scanned, it needs to be as close to real time as possible. So we scan, we raycast to unwrap, because the topology of the LEDs on the head is, let's say, of cylindrical shape, more or less. You anchor certain features with, like the eyes, nose, mouth, ears, with some sort of an ICP and nonlinear registration. Use optical flow to stabilize in the same way that a camera would use it. And then for the rest of the body, we would use optical, a uniform mesh, but it only needs to happen once every 20, 30 frames. So it's okay for that part not to be purely real time. And then we have a 2D to 2D. So I can show you what the giant looks like. So this is a mock-up. At the background, you see a head. This is live. This is made out of LEDs, but this head is going to be bigger and it's going to stand on the giant. And on the left, you see the ring. So people would go in there and say their message, and then we get this thing mapped. I only have a very small clip of what the... Yeah, so this guy is talking. He only did this for 5 seconds, but you can see how hard it is that I have to map his eyes perfectly at the right spot. Otherwise, it will be on his nose, and that's a big problem. And Gizmo is a tool I've been writing pretty much on my own. It's something I want to finish and give it to the people who are using the ring. It's what you see is what you get tool for editing the solve. Solve is the final mesh that you get out of the ring with the textures and so on, the geometry and sound. So what I want to do a few simple things that nowadays are very hard to do in the ring, such as reorder and combine and remove frames, or mix frames from two different data sets. Do some operations on the data, such as color correction. So it's quite important. Some cutting, some reposition. And the very last thing I've been working, I think, what day is today? Is Tuesday. I've been working on it Friday, Saturday, is a relighting filter. So the relighting would so this is the gizmo as it looks now. As I said, it's a work in progress. So this is just scrolling through and showing some options of what one would be able to do. Then export, and then you can use your model. And this is the relighting. So the idea here is that you will have a virtual sources of light, like let's say this one, and it would perform a photon mapping simulation. So this would cast millions of photons into the scene, just like ray casting basically, and it would interact with the human body. So if you look under his arm, there is a shadow, and the light that comes in this example is purple. So we can combine all of it's a good idea. It's clever how it's solved. It's almost, I wouldn't say real time, but it's definitely getting very close to it, considering we're talking about here in this scene probably hundreds of millions of photons being cast, and this is on my computer. My computer is very, very old. So you would have this ability in Gizmo to relight the model, add more ambient occlusion, all of these things. So, and that brings me to the end of my presentation. Hopefully, since I'm staying in your city until Friday, I will have some more time to speak to you in a lot more detail on some of these things, and maybe we can arrange to talk to you about my my hobby, which is something else that brought me to Finland already in my life, 8, 9, 10 times to Helsinki before. That I think that you would find very interesting. But that's it for now. We can have a few minutes for questions. Am I right? Yes.
Yeah. Now we are going to get questions from the audience.
Yeah, just a stupid question. What was your hobby? I was curious.
My hobby is demoscene. I don't know if you've ever heard of that.
Which one?
The demoscene.
No.
The demoscene. Okay, in 2 words, we make real-time content. So it's a computer program that you run on a PC or PC, and it shows graphics. It shows our ability to make real-time graphics, just like in a game. But we also have to make our own music and our own graphics and code and direct and everything. And what you present to you go to these things called party, which are basically competition. So people from around the world that have groups, they do that. And you go there and present something 4, 5, 6 minutes of content, and people vote on artistic and technical merit. And it has the roots, goes back to the 80s. And I've been involved with it, getting to 31 years now. So I have, quite a lot of material. And Finland has probably the biggest and the most, definitely the most famous demo party ever. Has been running for 30 years in Helsinki every summer. And I have quite a lot of content. So another day, maybe I can show you a lot more, and I can discuss how I do these things, because some of it, most of it is hacks, computer graphics hacks. But we do all of this, we don't do it for money. There's no money in it. So this is why it's a hobby. It's not a profession like what I'm doing now.
Okay, thanks. Sorry, everyone, if somebody had some kind of technical question. I was just interested.
Maybe a question from my side. What is the state of this Gizmo? Is it going to be publicly available or open source? Or
publicly available. I'm trying as hard as I can to finish. It's a very big. It's a big application. I'm at the stage. It is working. But you have to consider that all the different options for export and import and sound there's a lot of little things that need to work very well before I can say, okay, here you go. And I want the first version to do 10 things, but I want them to do well and just works. I've done some other applications that I've been involved. You may are already using it, like the MVX player and Genesis. Maybe you've heard of them, maybe not. But this. The last thing that I showed you with the photon mapper is the Genesis, that's our filter building pipeline. Some of the other stuff where I had meshes running around and playing, this is the MVX player. I want it to be scriptable, and that's another challenge, is that what comes out of Gizmo is not just, okay, I did one thing, but a script that you can put it to other files and do the same. So it's a kind of hybrid between a scripting engine and a simple what you see is what you get application. So I'm working on it, but it's hard work. Yeah.
Okay, thank you. Last chance for questions. Yeah, let's move the mic.
Thanks. Hello.
Hello.
Sami here. If you would need to solve the problem that some of the biggest artists in the world would like to cut their live show, digitalize on the virtual reality in a live, for example, Metallica or somebody, and you would there is no limit on the money, and you would need to solve it, that how you could make their live show on the virtual reality, how you would do it.
How? Sorry, I didn't quite understand the first bit. What?
Metallica live music show. Artist called Metallica, you know.
Yes.
Yeah. If they would hire you,
Yes.
and you would need to solve to make their live show at the same time when they're playing live to the virtual reality.
This is
How you would solve
actually
it.
we have done things with artists such as Metallica. I can't say which one, but very famous. Now the problem was that they were not live on the stage; they were in the ring. And the limitation of the ring is, of course, the size. Now, if you were to do it, let's say on a money no object situation, I think it's very much possible. The more tricky thing would be how to enlarge the ring enough so that they can be in there and have a space of 3 or 4 meters. However, we have the infrastructure to do quite a lot with photogrammetry that doesn't require things to be so close by. And I would say that at this case, and I don't have the figures, but the depth sensors would need to be changed so that they may give a, let's say, worse quality because of the distance, and there is no, as far as I know, there is no perfect solution for something that is 5 meters away to record with any of the technologies that I've mentioned at the beginning. But to combine that, so you would lose something, but if you have a lot of processing power, then you would be able to recoup that using photogrammetry, I believe. Now, the problem there would be how to do it in real time with photogrammetry. So you would need to up the computers and so on. So the ring is not what can be done without a limit. So if we didn't have a limit, and you could have, let's say, super fast cloud processing, there's a lot more that we can do, speed, sizes, etc., etc. But if you want to keep the cost down to low hundreds of thousands, let's say, dollars, then, for example, you don't want to be sending things to the cloud. You want to processing all of the. You don't want to have lots of racks of supercomputers running. You know, then it becomes this thing that you have. But it can scale quite a lot. It can scale quite.
But you could do that on the real live stage.
I believe so. Yes. Yeah.
With the live lighting, not the special like studio lighting, but like
concert
lighting.
The lighting hasn't really been a big problem for that. I have seen the ring working with very poor lighting conditions with a LED wall. You know, an LED wall would be something like a cylinder made out of LEDs around you outside the ring, and so the idea is that So this is Hollywood, okay? So this guy, he's walking on the treadmill, and then there is fire. You know? So the LED is red. So he's recorded as if he's in fire, and then he's put into the scene, and it works really well. So it's not that you need these sorts of lights for everything to work. No, I think that the problem with what you suggest is how well any depth sensor would work from some big distance, as in 5 to 10 meters radius.
This is a fruitful discussion for the coffee break. Yeah, so thank you.
Maybe
Thank you,
so.
Kostas, once again.